Hello, this is question 7 from the 2014 maths. So a finite automaton is a mathematical model of a simple computing device. A small finite automaton is illustrated below, whatever that ends up meaning. I assume that's what the text is describing. A finite automaton has some finite number of states. Right, they've mentioned finite 4 times already. So I'm going to circle that because that seems to be important. The above automaton has 3 states, so S0, S1, S2, right, the 3 things in the circles. Although S1's got a double circle, interestingly. Initial state S0 is indicated with an incoming arrow. Yes, off here. The automaton receives inputs, e.g. via button presses, which might cause it to change state. In the example, the inputs are A and B, so all of these arrows are just telling us how to wander around. State changes are illustrated by arrows. Yes, for example, automaton's in state S1, it receives a B, it changes to S0. Yes, it follows the arrow. It's in state 2 and it receives either, it stays in state 2 because they both just curve back on themselves. For each state, there is precisely one outgoing arrow for each input. Some of the states are defined to be accepting states. Okay. In this example, just S1 is defined to be accepting as represented by the double circle. A word is a sequence of inputs. The automaton accepts a word, W, if that sequence of inputs leads to an accepting state from the initial state. For example, the above automaton accepts the word ABA. So if it was ABA, it would go S0 to S1 to S0 to S1. It ends on the accepting state, so it's an accepted word. Fair enough. Write down a description of the set of words accepted by the above automaton. A clear but informal description will suffice. So we must end at S1. That's what they've told us. Not I, S1. So therefore, to end at S1, the last letter must be an A. So that's a good start. Then what else are we going to do? Well, we don't want to go to S2 because you can never leave. We can't go to S2 because there's no escape. So if we're at S2, we have to start at S0. Start at S0. We can't go to S2, so we must go A. So we need to start with A. And then so if we're at S1, we can't then do an A. So S1, so from S1, we must end or go B. Right, so we're starting with an A, and then we either just end, or we have to do a BA, and then a BA, and then a BA. Right, so we go, so the accepted words are A followed by multiples of BA. So we could have A, ABA, ABABA, ABABABA, that sort of thing. Right, that was good. Part 2. Suppose we alter the above automaton by swapping accepting and non-accepting states. So we make S0 and S2 accepting, but make S1 non-accepting. Okay. Write down a description of the set of words accepted by this new automaton. Again, a clear but informal description will suffice. Right, this seems quite straightforward. So they are just saying now we don't want to end on S1, we want to end on S0 or S2. Okay, so we must end not on S1. So it's going to be anything that doesn't end on S1. So therefore, set of words. So yeah, the accepted words are any words not in the set defined in part 1. Classic coding logic. You're either at S1 or you're not. Right, so that's part 2. There's plenty more of this. So it's so wordy, this question. I have to cut it across 2 again. Part 3, draw an automaton that accepts all words containing an even number, possibly 0, of A's and any number of B's. So we have to have both. So an even number of A's and any number of B's and no other words. Right, well, we know we come into S0. So let's draw that on first. So that's our S0. And we're coming in there. Now, whether that's going to end up being an accepting state or not, we'll have to see. So we want an even number, possibly 0, of A's and any number of B's. So as we come in, well, that could be it. We could just have an empty word. So that is fine. We have to make that accepting to cope with that empty word. Then we want an even number of A's. So we got to leave with A, because if it loops back on itself, we're just going to end up getting an odd number of A's. So it's got to leave. So let's take that off to S1. Now, if we did an A from S1, then we have to go back. Well, we could go back to S0. It just depends if we have to have another accepting state or not. Any number of B's. Any number of B's. So, well, B is then, well, if it goes, it's got to go off to another accepting state, or maybe the same accepting state. Can we just loop ourselves here? Just thinking, if that did that for B, so we just keep coming back. It doesn't matter what we're doing with B's, and we do that with A. So that means we're always going to get even A's because we have to go out and back. So we're doing A's in pairs. We're doing B's just on their own, round to S0. So what do we do with B coming out of S1? So it can't go back to S0 because then we'd have an odd number of A's. But it can loop to itself as well. So yeah, we do that for B as well. Yeah, that works fine. So we can just amass B's wherever we want. The key thing is we got an even number of A's. Right. Okay, part 4. Now draw an automaton that accepts all words containing an even number of A's. Okay, we know how to do that. Or an odd number of B's. Right, so we might have options where we've got an odd number of A's then, if we've also got an odd number of B's. Right, I get the feeling this is going to be quite tricky. So we've got S0, which we know has to be an accepting state because we could come in with nothing again, which is an even number of A's. So if we want an even number of A's, then again, we want to head off to S1, but we have to leave. We want to leave with B as well. But we go off with A to S1 because we can't have A going back to itself because the same reason as before. So it can't loop round to S0, so it's got to go somewhere else because otherwise we'd have an odd number. S1 then cannot be an accepting state because at the moment we got an odd number of A's and an even number of B's. So that can't be accepted. So we can go back to S0. I mean, that seems sensible to go back there with A. So that's fine. But if we've got, what do we do with B's on this? So a B, we need an odd number of B's. So it could come back to itself. But we have got the possibility of having odd B and odd A because we've got an OR in this. So we could take B back with S1. That could give us odd A's and odd B's. But is it going to give us, and it gives us even, it's not going to give us all the options though, is it? Because if you then have a B, you'd have to have an odd number of A's. And we can't loop B back to itself on S1 because then we would have an odd number of B's and we're not on an end point. So it's got to go somewhere else. just through a process of elimination. We can't loop back on itself, as I say, because we wouldn't have an end state, even though it's a valid word according to those criteria, and we can't go back to S0 because we're not including all solutions. We wouldn't be able to have even and odd. We've got even and even, or odd and odd. So right, so it's got to go off this way for B to S1. So it's coming into then, well, let's call that S2. And S2 then, so would that be valid? Well, yeah, that would give us an odd number of B's. So that's going to have to be an end state as well. And we've got that's always going to have, at the moment, odd B's. This is always going to have even A's. So we've got odd B's, we've got even A's. So now we need to add even A's to our odd B's down here. So we are gonna need a fourth one, aren't we? Because we can't go back over here. We need to have a fourth one. This is always going to be, this is our way of generating even A, and then, yeah, okay, right, I've finally seen how this is working. This is all coming in now, because we got permutations here. We can have even A, even B. We can have even A, odd B. We can have odd A and odd B, because in these two cases we've got even A's, and in these two cases we've got odd B's. So we need three different end states depending on which one of those combos we've got. So we will need a third one in there, S3. So this is even A and what? Well, we'd have to have B going out and back. That's going to be even A, even B. This will be odd B and even A. So now we want to get I've written these the wrong way around. So that's going to be odd A. The wrong way around as in I'll put A at the top there and I'll put A at the bottom over here. But we had two even A's. So that's going to be our odd A, odd B. So we have a B come in and we have a B go out. So that keeps us even B at the top and even A at the top. We'll have then down the bottom here, we've got, no, that's not right. That's even A, not odd A. Yeah, we'll have even A and odd B. So, oh yeah, we've already picked up an A going via S1. So that's going to be an odd A. And then we do the old A loop thing there, A and A. Right, okay, yes, yeah, that makes sense. It would have been easier if I picked up those combinations before. So the fact that we have to have three different end states, even A, even B, even A, odd B, odd A, odd B, that's three different end states that we can have. Whereas here, we don't have any options. We have to have even A. Nothing else really matters with the B's. You can have any number of B's, so whatever. We've just got one setup, one set of criteria for the end state. So we only need one end state double circle. Whereas here we've got three possibilities, so we just have different ways of navigating around them. Well, that was really clever question. So, but yeah, it took a while to see it. I mean, it's impressive. If you spot that right from the beginning, that we have to have those three end states, then yeah, impressive work. Right, last bit then. Let A to superscript n represent n consecutive A's. Right, let L be the set of all words that have to form AN, BN. Right, n starting from 0 going upwards. All words composed of some number of A's followed by the same number of B's. We'll show that no, oh, here we go, we're back on finite again. Finite automaton accepts precisely this set of words. Right, so they told us what we're going to try to do. Suppose a particular finite automaton, they're really stressing the finite again. You know, notice they dropped it in the previous parts here. but now they brought it back again. So there's going to be something to do with this finite. It's got to be. A does, oh yeah, suppose a particular finite automaton A does accept precisely the words in L. Show that if I is not equal to J, then the words I, J, AJ must lead to different states of A. Right, so that was quite a lot to take in. So a finite automaton does accept precisely the words in L. So let's note some of this down then. So A accepts precisely the words in L. So only words in format, so A, N, B, N. So that's all it's accepting. Show that if I is not equal to J, then the words I, AI, AJ must lead to different states of N. So we've got an AI and an AJ. So we've got A accepts only words in that form. So we can AI and BI is accepted. So, and we want to must lead to different states. Right, so that goes to an accepted state. So we know that much. We can also say then, so for AJ, so AJ BI can't go to an accepted state because it's not in that format. So not accepted state. So we've ended up in two different places, but I haven't done what they've asked because they want to know, show that that the words AI and AJ, so without the BI bit, must lead to different states of A. But we're doing BI off the back of both of those. So therefore, let's do another therefore. If AI and AJ were leading to the same state, then AI, BI and AJBI would also lead to the same state. Okay, so that's shown that they're different. Therefore, AI and AJ lead to different states. Right, so far so good. Hence show that this leads to a contradiction, is what they're saying here. So we still haven't used this finite bit. I mean, I've just got this finite in my mind now because they keep bringing it up. They still haven't done anything with it. So we want a contradiction in this to show that this doesn't work. So something has got to become infinite. So AI and AJ lead to different states. So for every value of N, we're getting a different state. There we go. That's our contradiction then. So AN leads to a different state for every value of N, which is an N is just going from 0, 1, 2 all the way up to infinity. So therefore we got an infinite number of states. So, well, I've run out of space now. So I don't know where I'm going to put it. Let's just write it here. Infinite number of states, which contradicts so not a finite automaton. So we finally got that finite bit comes into play. Okay, right. They're kind of waiting on that. I mean, they've been just dumping finite in all over the place, and because they dropped it, it just made it even more suspicious that they weren't talking about it in the middle of the question, having stressed it so much at the start. I would say that was a tough question. It was a very fun one. It started okay-ish. I mean, it was still quite difficult at the beginning, and drawing these pictures weren't simple, particularly the second one. Until spotting this pattern, it makes it quite difficult to see which way to go around everything. But once I got that in there, actually I can just see I've not added That's not complete. I've not got a B line coming out of S2. So where would that go? Well, looking at the symmetry of it all, I'm assuming it's going back to S1 because we have to have odd B on this side, so it can't be going to S3. So yeah, I need another line. Yeah, missed that first time through. But yeah, I suppose that's recapping questions for you, isn't it? Just having a look at the end at what each part of the question was like. So yeah, you might have spotted that on the way through. Yeah, I would say that was quite difficult all the way round, that one. But it's been a really fun paper this year, 2014. They have up and down years, but this one's been one of the good ones. I really like the last question as well, question 6. So yeah, hopefully 2015 will be just as good.